Okay, so I'm going to go over second order differential equations, mostly focusing on the reduction of order. So this is kind of hefty to get where we're going to go, but it's easiest if we just do this with examples instead of trying to explain the theory, and it'll kind of make sense as we go. So we're going to start by looking for differential equations of this form. So we want y double prime with a coefficient of 1, and then we want our y prime to have a coefficient of just some function of x or a constant or nothing. It can be not there as well, but this is kind of ideal as if we have p of x times y prime. And then we want the regular y term to also only have a coefficient of x's. And then we want this all to be equal to some function of x or constants, right? This is what we call linear. So this is kind of the ideal situation. So we're just going to start with one case, a special case here. So if we have y double prime minus y equaling 0, this one's actually really straightforward and is one you could just memorize if you wanted to, but you can solve it too if you'd prefer. This one just works out to be e of x is equal to our first solution, and then e to the negative x is equal to our second solution. Now, what's interesting about this is we can still do some stuff here to make sure that we understand kind of what's happening and like how these things or what's important about these solutions. So one of the most important things is our solutions have to be linearly independent. And so the easiest way to check for that is to take y2 divided by y1, and that needs to be equal to some constant u, where u is a constant, right? Okay, and this might look a little familiar. So what we can do here is we're going to take e to the negative x, and this is e to the x here, and that should be equal to some constant. Now we can see over here that e to the negative 2x is what we're going to get if you flip this up to the top, right? And that's going to be equal to some constant. Yeah, okay. Okay, so what this looks like is because we've proved that this is linearly independent, we can now go ahead and write our final equation here, which is y is equal to c1 times y1 plus c2 times y2, which is, in our case, oh my goodness. So that in our case is going to be c1 times e to the x plus c2 times e to the negative x, right? And that is our general solution for y. Okay, actually I shouldn't have been saying constant. This should be u as a function of x. Okay. Where u function of x is a constant. Yeah, okay, we're good. Both those things are true. Okay. So next we're going to work on just a quick example where we're actually going to do an initial value problem. So in this one we're going to take that y double prime minus y equals 0, and we're going to have y sub 0 is equal to 4, and then y prime of 0 is equal to negative 2. Okay, so we already know our general solution for y is going to be c1 e to the x and c2 e to the negative x, right? We already know that's true because that's the rule we just saw. So now what we can do is we can just go ahead and go straight into our initial value problem solution here. So we're going to say this y is going to be 4, and then everywhere we have an x, we're going to plug in a 0. Right? This is stuff we should probably feel pretty good at this point in the course. So we now have 4 is equal to c1 plus c2. And then we're going to do the same thing with our other condition here, except we need y prime. So we're going to take y prime of our general, which is c1 e to the x, and then negative c2 e to the negative x, right? Because derivative of e to the negative x is just negative e to the negative x. And now we can plug everything in here. We get negative 2 is equal to c1 e sub 0 minus c2 e sub 0, right? And so then we have negative 2 is equal to c1 minus c2. And then we can pick either of these to solve. So I'm just going to solve this right one for c1, because I just have to add over c2, so that just seems easier to me. And then I can plug this in over here. So I get 4 is equal to c2 plus minus 2, and then plus C2, right? Add the 2 over, so I get 6, and then I have 2C2, so C2 is equal to 3. Now we plug this back into our original, we get C1 is equal to 3 minus 1, so C1 is equal to, 3 minus 2, getting ahead of myself here. So C1 is equal to 1. And now we can plug it all back into our y, and instead of getting general, we're going to have a particular solution now. So we should have e to the x, and then plus 3 e to the negative x. That's it. Okay, so that's our initial value problem for this particular case. So now we can move on to our next case. So here, instead of having y double prime minus y, we're going to have y double prime plus y, and that's going to equal 0. So this one is already defined as well. We can just go straight to c1 cosine of x and c2 sine of x. Okay, this one's also one of the ones that's just already defined. So we can do our y1 divided by y2, and that equals cosine over sine. I'm realizing now I was saying it's supposed to be equal to a constant. It's supposed to not equal a constant. That's what I meant to be saying. So I will make a note of that. But yeah, so this y1 over y2 or y2 over y1 should not equal a constant. And it doesn't really matter which one you do, y1 over y2 or y2 over y1, for the purposes of just checking that. It does matter later when we do the integrating factor, but we'll get there in a minute. Okay, so that's all we need to check here. The solution is valid because it's linearly independent and it works for the cases, so we're good. So we'll come back to something that looks like that here in a little bit, but we're going to go ahead and move on to what I was just talking about, which is the integrating factor for second order. So you're already familiar with this from your first order. Now we're going to apply it to a second order. Okay, so sometimes we're going to have our differential equations where we're going to know one solution. So let's say we still have y double prime plus y equaling 0, and they tell us that y2 is equal to, in this case we're not getting told exactly what it is, so we're just going to say it's equal to u y1. Okay. So then all we have to do is we have to take two derivatives of y2 so we can plug it into our original formula. So we're going to get y2 prime is equal to u prime y1 plus u y1 prime, right? And then our y2 double prime is equal to u double prime y1 plus 2u prime y prime plus u y1 double prime, right? Then we can plug it in. I'm going to skip all of the algebra of plugging that in and just go to the next step, which we're going to have simplified down to u double prime plus u of prime, and then that's going to equal 2 times y1 prime plus p of y1 and divided by y of 1. Okay, and all of that is still equal to 0 because our original was still equal to 0, right? We didn't change anything there. So now the next thing we're going to do is we're going to say, okay, we're going to let w equal u prime. So then w prime is equal to u double prime. And so this is how we get to our reduction of order form. So now our w prime is replacing our uw prime, or our u double prime, and then our regular w is just going to replace this u. So we have plus, and then w. And then we have all of this junk inside. So we're going to have 2y1 prime plus p of y1 over y1. Okay, and now we're in that form where we can do separation of variables. So I'm sure you remember separation of variables. So I'm going to just rewrite this first piece a little differently so it's a little more obvious what we're doing. So we have dw divided by dx plus this equals 0, so we can subtract over and then move stuff around. So we're going to get to a form where we have dw over w is equal to negative 2y1 prime plus py1 over y1, all in parentheses, and that's all dx. Okay. And so now we already know what we're going to do here. We're going to integrate both sides. We're going to get a natural log over here. We're going to take an e to it. So we're going to get w is equal to e to the negative integral of, we're going to put all of this stuff and just call it p of x. And then that's dx. And then all of this is divided by y1 squared. And so this is the part that you need to remember. You don't need to know how to get here. That all is just to show you kind of the intuition behind what's going on. This is where it gets important, but this is actually not the final form yet. So what we actually have here is just part of our integration factor. So here we have to say, okay, well, y2 is actually equal to y1 times the integral of e to the negative integral p of x dx over y1 squared. Okay? And then you have a second dx as well. Okay? So now that we've kind of figured out how this is going to work, let's do a couple just to make sure we feel okay with it. So, switch colors here. Let's try this one. So we have x squared y double prime minus xy prime plus y is equal to 0. Okay? Now, we already have a problem. We can't even start this one yet because we have this x squared in front and we need this to be a 1. So we have to clean this up first. We're going to divide everything by x squared. So we'll get y double prime minus y prime over x plus y over x squared equals 0. Now the y over x squared is not a big deal. We're not worried about that, okay? The other thing we were given when we started this problem was that y1 was equal to x, okay? And so now we can see pretty clearly our p of x, this isn't given, but we can see what it is. It's negative 1 over x. So I have negative 1 over x, okay? So now what we're going to do is we're going to take our negative integral of that, right? And so negative negative cancels, integral of 1 over x is equal to natural log of x. So now we have y2 is equal to integral of e to the natural log of x divided by x squared. And then that's dx, okay? And then we're going to multiply by our y1 out here as well. So now we have x, and then this is just going to be x here, so we have integral of x over x squared dx, which we can see is just 1 over x, and we already know that's natural log of x, so we get x natural log x. Okay? And so then all we have to do is just write that that is our y of 2, because that's all we were asked to do. We don't have to write our general form or anything else. So we're done. Okay, let's just do one more example. If you use the Edwin Kriegsing book, this is section 2.1, question 11 of the homework. And this one is going to be x squared y double prime plus xy prime plus x squared minus 1 over 4 times y equals 0, where y sub 1 is equal to the square root of x times cosine of x. Now, we're going to do the same thing we had to do last time and divide our y squared through. So we get y double prime plus y prime over x plus x squared minus 1 over 4y divided by x squared, and all of that equals 0. Now I know this term right here looks really, really gnarly, but it doesn't matter because we don't have to worry about it. We don't have to deal with it. It's all good. We're only worried about this p of x right here and our initial given solution. So what we can do now is we can just do exactly what we just did earlier. So we get our p of x is equal to positive 1 over x this time. And we're going to take the negative integral of that. So we already know this is natural log. So we're going to get our integral here is just going to be equals to negative natural log of x. Come on, tablet, scroll. There we go. Okay. And now that we've done that, we can go ahead and write y2 is equal to our y1, which was square root of x cosine of x, times the integral of e to the negative natural log of x divided by our square root of x cosine of x squared, and all of that dx. Okay? So this one's just a little bit of algebra and a little bit of trig, but we'll get there pretty quick. So we got root x cosine of x, and then all of that is times e to the negative natural log of x. Natural log and the e cancel, so your x drops down as your argument, but that negative 1 is still there. Please don't make that mistake, y'all. So this is x to the negative 1. And then on bottom down here, we're going to have x times cosine squared. So we get x to the 1, and then cosine squared of x. And then the dx is gone because we just took the integral, or no, so sorry, we still need to take the integral. So we have dx still. Now, x to the 1, x to the negative 1, one of these will go down, one of these will go up. Hold on. Oh, shoot. This is supposed to be negative. Sorry. This is to the power of negative 1/2, and I was just translating it. That is my bad. I was translating it wrong. Okay, there's that, which means all of these are wrong also. Sorry, y'all. That's what happens when I try and do too many of these too quick. Okay, there we go. All fixed. Now this makes more sense because we have negative 1, negative 1. Those are just going to cancel. So we get integral of 1 over cosine squared. So we have equals x to the negative 1/2 cosine of x times, now, integral of 1 over cosine squared is the same as integral of secant squared, and the integral of secant squared is just going to be tangent of x. Okay? Now, what's cool about tangent of x is we also know that tangent of x can be rewritten as sine cosine. So now I have this stuff all equaling x to the negative 1/2 cosine of x, and then sine of x over cosine of x. And so our cosines will cancel, and we're just going to get x to the negative 1/2 sine of x, and that equals y2. Okay, but that's it. Sorry for the mistake I made copying the problem over, but this is the correct solution, so we got back to where we were supposed to be.